I'm sure you all know Dr. Drake Harmon. Today he is going to be talking about algebraic geometry with us.
This is the kid that puts me on the science club group chat.
It is. So we're going to talk a little bit about, sort of the building blocks of algebraic geometry. Algebraic geometry is an advanced mathematical field that puts together a number of mathematical fields. And so it's this way where if you want to talk about algebraic geometry at all, you have to spend a lot of time talking about definitions and terminology and so on from these various fields. For example, my dissertation that I wrote is in a specific example in algebraic geometry. I think the first 15 pages or so of it are preliminary definitions that you need to know before you even begin discussing like what's happening. I've tried to make it presentable and digestible here. Hopefully I've done a good job. See if anybody has questions about anything I say as I'm going. Feel free to ask. Answer as best as I can. Okay. So what is algebraic geometry? So it turns out that there is a very rich and strong relationship between the structure of, so this is something that is probably relatively familiar to a lot of people, the idea of zero sets of polynomial functions, right? If you've taken maybe like pre-calculus, college algebra, right, you do questions where, you know, they ask you to find, and I'm just making up some numbers, I'm not going to solve this. You know, here's a system of two equations, right, in two variables, find the point x, y that satisfies that system, right? So whatever point x, y that makes that system work, in this terminology, I would refer to that as the zero set of that system, right? The set of common zeros of those polynomials. We know that for linear polynomials, right, there's not that many choices for what the common zero set can look like. If your polynomials are linear, you learn that you can only have one, the common solution set, zero set, can be 1 point, no point, or an infinite number of points. But as soon as you start allowing nonlinear polynomials, your solution sets can look like, you know, whatever, right? So y equals x squared is a polynomial, right? I don't know, here, let's say, right, so here's a couple of nonlinear polynomials, for example, right? So still polynomials, but not linear because of the second powers, right? I don't know, how big the radius of the circle needs to be, right? But you can, as soon as you have nonlinear stuff, right, you can have curves intersecting at a certain number of points, right? And you can get zero sets of sort of any structure that you could possibly imagine based on the polynomials that are involved. And of course, you can solve systems of equations that involve more complicated formulas, functions than just polynomials. But in algebraic geometry, we focus on polynomial systems of polynomial equations specifically. So let's start by defining some terminology from a couple of areas of mathematics. Okay. So we want to start with a set of numbers. I'm going to refer to it as k here. So I'm going to start with some definitions from geometry. So the geometry that we're referring to here, by the way, is not geometry like, you know, oh, angles and triangles and circles and shapes and stuff. When we're referring to geometry here, I guess I have an image. Let me scroll a little bit ahead. So we're talking about these common zero sets of polynomials, right? So I'll go back to all of this in just a second. Right, but the geometry that we're referring to, right, we can have something like this. So in three-dimensional space, This one in red is the graph of this 3-variable polynomial. This flat plane in blue is the graph in 3 dimensions of that polynomial. And then where they intersect, this sort of parabola in green that's running that way is the common, that's the set of intersection points of those two graphs, which is the same thing as saying that would be the collection of points in 3-dimensional space that make both of these equations true at the same time. That green parabola is the common 0 set of those two polynomials. So when we're talking geometry here, that's what we're talking about. The structure of the set of common zeros of some collection of polynomials. What can we say about the structure of such a set? So now let's back up here. So some geometric definitions. So I am going to use the letter K here to denote a set of numbers. That's a little bit vague. Later I'm going to talk about some algebra definitions. Specifically what we are going to want, and we'll define this in just a little bit, so I assume most of you probably know what it means right this second, but that's okay. We're going to want K to be what is referred to in abstract algebra as an algebraically closed field. I'll talk about what that means in a little bit, but there is at least one example that a lot of you are probably familiar with. The set of complex numbers, right? Right, all the numbers that look like A plus BI, right, where A and B are real numbers. That is an example of an algebraically closed field. Again, we'll define what that means in a little bit, but for now, if you want to think of this K as just being the complex numbers or something, that's fine. We define affine in space over this set K, which is denoted as either, so a lot of sets in math use this weird bold symbol notation, so the set of complex numbers is like that, the set of real numbers is this weird, I didn't draw it very well, but this weird R here, right? So that this weird A here, I just, so this notation is meant to denote what is called affine in space over K. So essentially that just means the set of all intuples of elements of K. So if I have for example, affine 2 space over the complex numbers, what do I mean by that? I just simply mean the set of all possible ordered pairs of complex numbers, right? So maybe it's a bit more of a weird sounding word than it really needs to be for what it's defining, right? But, right, so like affine 2 space over the complex numbers, right? The set of all ordered pairs that look like one complex number and like another complex number, right? So 2 space, 3 space, 4 space, in space, ordered pairs, ordered triples, ordered intuples, right? However many components you want in your point.
So there's no harm in thinking about an n-tuple as a ordered list of numbers?
No, and in fact, the individual elements, just like you might in whatever other math class, the individual elements of the affine in space, we just call it the points of the space. So the same way, the real numbers are not an algebraically closed field, but just sort of to use them as an example here anyway, right? Affine 2 space over R, that's essentially the same thing as like the XY plane, right? Ordered pairs of real numbers. Yeah.
What does R to the n mean?
So to R to the n.
Yeah.
So that notation it's basically the same thing. So if you write something like R, like sort of set of real numbers, right, and you write n, that means essentially the same thing as if I were to say affine in space over the real numbers. That is to say, it's the collection of all possible ordered intuples where each of the r's has to be a real number. The reason for and you may argue that like there's not really much reason to quibble between the difference between the two. The reason that's often given for like the different name of affine in space versus like something like Rn or whatever is that something like Rn, you take a field, again, we'll define what that means in a little bit, like the real numbers, and you have a collection of points like that, you can define an algebraic structure on such a set, make it into a vector space, essentially, right, where you add vectors component-wise, you multiply a scalar by a vector the same way you would do if you learn how to use vectors in trigonometry or something, right? Affine in space essentially is the same thing, but you forget the algebraic structure. You sort of say, forget the vector space stuff, forget all that, I just want to consider the set of points, and that's all I care about. I guess another thing I'll say really quickly, we're not going to bring this up at all, right a second, I just in this talk, but affine in space, another reason for the term affine space is as opposed to something that is referred to as projective space. So like, I won't talk about that really at all in the rest of the talk here, but affine in space is sort of like closer to like a standard, like your XY plane or something. And then projective space is sort of, it's hard to explain, I guess, like kind of an extension of that to where it's sort of like what the assumption that parallel lines are now intersecting each other at infinity or something like that, right? So one reason for the word affine is like, okay, forget the algebraic structure. Another reason for the word affine is if you're trying to distinguish between, are you talking about in-dimensional affine or projective space? Again, we're not going to talk about projective space, so the distinction won't really be important here, but.
So, in essence, I guess, if you were to have a point that belongs to, let's say, r to the n, that point is in a n dimension?
R to the n? Yeah, R to the n is an in-dimensional space. Yeah.
Okay.
Right, so like essentially like if you've taken like, you know, like calculus 3 or something, right, and you're doing a lot of stuff where like, you know, you have x, y, z axis, right, and you're graphing and drawing surfaces and stuff, that is a visualization of R3, three-dimensional real space. Okay, so we have that one. Okay, so we want to talk about polynomials, right? So there is a notation so we have our set K, again, you know, if you want to think of K as a complex number still, or it's just some whatever set of numbers, fine. We can talk the notation for, so if I write something like this, K bracket X, that's the notation that stands for the set of all polynomials in the variable X with coefficients that come out of whatever that set K is, right? Right, so for example, you know, I write a polynomial like that, right? The coefficients are all integers. The symbol for this set of integers in math is this one here, like a Z. I think it's because, is it the German word for integer starts with a Z, I think?
Yep.
So, like, I would say that this polynomial, for example, is in the set Zx, right? It's a polynomial in the variable x, and its coefficients are integers, right? So that's what that notation means. If you want to talk about multivariable polynomials, you can list all of the variables there, right? So if I have, you know, 5, just to make up some number, you know, 5/3 x squared y plus, you know, 1/6 x squared y squared z to the, whatever, I don't here's some binomial with two terms, right? That would be a polynomial, 3 variables, x, y, and z. The coefficients, I would say, are like rational numbers, right? So I would say that that would be an example of a polynomial whose coefficient comes out of the rational numbers. That's the symbol for the rational numbers in math. And x, y, z are the variables involved there, right? So that's our notation for, okay, you have a set of numbers. If you want to talk about the polynomials with coefficients that come from that set, that's the notation that we use. If you have a polynomial, right, so you have this polynomial here, whatever, you can view a polynomial with, so polynomial with n variables here, you can view a polynomial with n variables as a function from affine in space to the set k. And the function is just given by evaluating the polynomial, right? So for example, let me not use that one because the variables and powers are annoying. So here, yeah, let's just write down a similar polynomial, right? So, I don't know, here's a polynomial, right? With coefficients as integers, right? So this is a, zxy, two variables. So what this is saying is you can think of, in the way that you're probably used to thinking of it, you can think of it a polynomial, so for example, a polynomial in two variables. I could think of this, like let's say here, let's maybe name this like f of xy or something like that, right? Function of two variables. You can think of this function as being a function from affine to space to your set k. My set k on this example would be the integers, right? And the function is just like evaluating the polynomial at a given point, right? So for example, how does if I plug in, I don't know, 1, 2, right? That pair of integers to this polynomial, what does the function do? You plug it into the polynomial and evaluate it as you've always evaluated polynomials, right? So plug in 1 for x, 2 for y, right? So you want 6 plus 5, 11, right? So you can be, so polynomials are, I mean, that's probably not a surprise. I suppose polynomials can be viewed as functions, right? You plug in a point, you get an answer, right? So, right, so with a polynomial, you plug in a point, you get an answer. Sometimes you get 0, sometimes you don't get 0, right? If you're familiar with any study of polynomials at all, right, it's often, you know, when does the polynomial equal 0? That's often an interesting question for a variety of reasons, right? So we want to specifically interest ourselves in what are the zeros of the polynomial. So we have a notation for that. So if I have a polynomial f, then we use this notation, z of f. So z of f is, so we call that the 0 set of the polynomial f. So that is exactly as it sounds. It's all possible points in your whatever dimensional space you're dealing with, such that if you plug that point into your polynomial, you're going to get 0, right? So we'll use that notation to talk about the 0 set of a single polynomial. And actually, we're going to use the same notation to talk about the common 0 set of any collection of polynomials. So if instead of a single polynomial, right, suppose we have, right, our polynomial our polynomial set in however many variables there are, right? And we have some subset. So the symbol for subset is this one, right? That is, T is like some collection of polynomials, right? right? T is some set of polynomials, so it could be maybe just one polynomial, but you know, maybe a collection of more polynomials. Right, so if I have a whole set, so we can define the zero set of one single polynomial as we just did, but we can also define the zero set of this entire collection, T of polynomials, that is the set of all possible common zeros, right? So the set of all points, in your app, trying that A is really long. The set of all points in your affine space such that you get 0 when you plug that point into any polynomial in this set whatsoever, right? So Z of some set of polynomials is the set of common zeros of those polynomials. Right, so again, I'll go back to this slide, but again, just to bring this picture back up, that's what we're looking at here, right? We have one polynomial function, I said it was what, x squared plus y squared equals z, graphed in red here. You have another polynomial function graphed in blue here. The common zero set of those two polynomials, graphically again at least, is the same as the set of points where they intersect. So again, that's what we mean when we refer to the common zero set of a collection of polynomials. Obviously, if there's more than two polynomials involved, the drawings and visualizations get to be a lot more complicated than this, right? Okay, more definitions. So, if I have a subset of affine space, right, so Y is a subset of affine space, Y is some collection of points in your space, right? You call Y an algebraic set if Y is the zero set of some set of polynomials. So if Y is the zero set of if you can find some collection of polynomials where the zero set of that collection is these points, you call that collection of points an algebraic set.
Is there a requirement that to be non-empty?
No. There's no requirement that T be non-empty. If T is empty, then you would vacuously say, so there's nothing in T, I guess you would vacuously say that the zero set of the empty set is the entire affine space. And so the entire affine space itself counts as an algebraic set. Also, T could be, for example, T could be just like a constant polynomial, like 1, that has no zeros whatsoever, right? So the zero set of that would be empty. The empty set is also going to be an algebraic set. So all of the entire affine space is going to count as an algebraic set because it's the zero set of the empty set. And the empty set is algebraic because it's the zero set of any non-zero constant polynomial. So Y is called an algebraic set. So any set that is the zero set of some collection of polynomials, we're going to refer to as an algebraic set. So this here is just explaining the example on the next slide that I've already referred to a couple times right there. So couldn't really fit the explanation and the example on the same slide very well, so I just put the explanation there now. So anyway, okay. So I think that so that's basically most of the geometric definitions that we need here. I think kind of the basic geometric definitions you need here aren't that bad. I don't know if you would agree or not, but I think they're not that bad to understand for the most part what we're saying. Algebra, the algebraic definitions that we need are a little bit more involved, okay? So these algebraic sets, these zero sets of some collection of polynomials, those are the geometric objects that we would like to look at. Those are the objects that we would like to study. So now let's look at some algebra definitions, because what we would like to eventually do is come up with a link between the geometric properties of these zero sets and some algebraic properties of, well, some of the stuff we're getting ready to define. Okay, so a field, finally. So what is a field? So before so we can read the definition, and I think I say, or maybe a little bit later, some like familiar examples. But here, maybe let me write some familiar examples of fields first, and then let's read the definition. So examples of fields. So probably common examples that a lot of you would be familiar with. The set of rational numbers is a field. The set of real numbers is a field. The set of complex numbers is a field, okay? The set of integers is not a field, and we'll explain that in just a second. So a field essentially means you have two operations, right? You have addition and you have multiplication. And depending on how abstract you're going to get with this stuff, the addition and the multiplication can be like your regular addition and multiplication of like complex numbers and stuff. But you can do weirder stuff in abstract algebra where like you have a field of functions and the multiplication is really composition of the functions or something like that, right? So it doesn't have to be like a regular addition and multiplication as you normally think of it, depending on how abstract you want to get, but let's just, that's good enough for us for right now. So a field, you have a set of values, set of numbers, two operations that you generally refer to as addition and multiplication, and they satisfy, essentially they have to satisfy all of the common properties that you would expect addition and multiplication to satisfy in any of these particular sets. So I said it here, behave as similarly as they do for real numbers, but you could say for rational complex numbers. So specifically, so I say specifically, there's a whole list of things here that means, right? So the associative law, the commutative law for both addition and subtraction have to hold, right? So, right, the associative law for addition has to be true. The associative law for multiplication has to be true. The commutative law holds for both operations, right? You can add in either order. You can multiply in either order, right? There is an additive identity, right? Generally written as right, 0 plus anything gives you back the thing you started with, right? So there's some element like that, like 0 in your set. There's a multiplicative identity, some element like 1, where anything times 1 gives you back the element you started with. And you have to be able to find inverses, right? So like in, say, the real numbers, for example, right? Any number has an additive inverse, right? So if I write 7, what do I mean by additive inverse? Find me another number that I can add to this so that the result is the additive identity. So of course that's like -7, right, in the real numbers, right? And every non-zero number has to have a multiplicative inverse as well, something that multiplies it to give you 1, right? So 7 times 1/7, for example, is good, right? So those are multiplicative inverses of each other, right? So a field has to satisfy all of those properties, right? So you have addition and multiplication, and essentially all of the nice rules. I don't think I mentioned the distributive law holds as well, but it's right there. The distributive law, multiplication over addition, holds as well. So all of those familiar nice rules that you expect to happen in the real numbers. You have any set equipped with a couple of operations that accomplish all of those things, you call it a field. So now here I say it, right? Familiar examples of fields are the rational numbers, the real numbers, the complex numbers. There's other examples, way more abstract and whatever, right? But as far as stuff that you may have seen before.
This is kind of a dumb question, but does the vector field relate to any of this at all?
No, it's a good question, because there's no defined multiplication or inverses.
Yeah.
I mean, there's scalar multiplication, but you're not talking about
Yeah, because in a vector field, right, is like a function that takes what? Like if you're working, say, like three-dimensional space, right? You have a function that at any particular point in your space is mapping it to like some particular vector, right? So they call it a vector field. So I think that the use of the word field is more like you're looking at a field of vectors when you're sketching it out, so we're not attempting to use the word field in the same way. And I don't really think you'll be able to define like the same sorts of structures, like addition and multiplications. This is more like a function from one thing to another, where what we're trying to discuss here is a structure on one particular set, right? Even if you wanted to like attempt to do something, like you can add vectors, but there's not, I guess there's the cross product, but it wouldn't quite work for other reasons. But there's not really like a standard notion of what it means to multiply vectors and stuff, right? So in general, like even if you wanted to use three-dimensional real space with the cross product, even that wouldn't be good enough to be a field, because the cross product, I mean, among other issues, the cross product is not commutative, right? You get the negative if you reverse the order, right? So it's an unfortunate thing in math that they often use terminology and words, like the same word or terminology for two completely different things, but that's what they did, and we didn't get to decide that because they did that decades ago or whatever, right? So now we're stuck with it. I mentioned way back when we were first talking about that eventually what we wanted the set to be K to be a field, and we wanted it to be an algebraically closed field, right? A field is referred to as being algebraically closed if every polynomial with coefficients in that field has a zero in that field, okay? So that's an interesting definition. So for example, right, consider the polynomial x squared plus 1, right? That polynomial, I mean, so, you know, the set of integers is inside the set of rational numbers, which is inside the real numbers, which is inside the complex numbers, right? So like this, the coefficients are integers, right? So you can also call them rational numbers or real numbers or complex numbers. I want to call, let me say that, let me view this as a polynomial with real number coefficients. Right, so x squared plus 1 is a polynomial in x with real number coefficients, right? That polynomial does not have any real zeros, right? Right, the solutions to the equation x plus 1 equals 0 are x equals plus or minus I, the imaginary unit, which are not real numbers, right?
Yeah.
So x squared plus 1 is a polynomial with real coefficients, but it does not have any zeros in the real numbers. So that means, so that is an example that shows that the field of real numbers is not algebraically closed. Algebraically closed. Right, because you can have polynomials with coefficients in R whose zeros exist in a field bigger than R itself, right? So a field is called algebraically closed if that can't happen, right? If whenever your polynomial has coefficients in that field, its zeros are in that field. If
Is that all of its zeros or just at least one?
Well, you can say it in a couple of different ways, right? So the way I have it typed here and the way it's often phrased is that a field is algebraically closed if every polynomial with coefficients in that field has at least one zero in that field. But if you have a polynomial, right? So you have a polynomial, so you found 1 0 in that field, right? The factor theorem for polynomials says you can then factor out x minus whatever that 0 is, and you're left over with like a 1 degree smaller polynomial. that would still be a polynomial with coefficients in your algebraically closed field. You could reapply the same notion of it being algebraically closed to say that that one has a 0. And so the statement that there has to be at least one 0, if you just factor and keep applying it, that actually implies that all of the zeros of that polynomial have to be in the algebraically closed field. So if anybody remembers from algebra, there is the statement that is referred to as the fundamental theorem of algebra, right? Which can be phrased many different ways, but one way it's phrased is that every polynomial with coefficients in the complex numbers has its zeros in the complex numbers. So with this terminology, the fundamental theorem of algebra can be restated as saying the set of complex numbers is an algebraically closed field. If you have any polynomial whose coefficients are complex numbers, all of the zeros must be complex numbers. There cannot be any 0 that exists in some bigger space that you need to find, okay? So, not the rational numbers, not the real numbers, the complex numbers are an algebraically closed field. Okay, so related to the definition of a field is a structure called a ring. So a ring is essentially a field where you relax a few of the requirements. So a ring is a field, so you still have addition, you still have multiplication. You get rid of the requirement that so multiplication no longer has to be commutative in a ring, so maybe multiplying in different orders gives you different answers. So for example, the collection of say 3 by 3 or whatever dimension matrices, right? You know you can add matrices, you know you can multiply matrices, and if you multiply them in opposite orders, you don't expect to get the same answer, right? So you have a multiplication, you have an addition, that you could call that set of matrices a ring. It would be an example of a non-commutative ring, a ring where the multiplication actually is not commutative, the order matters. All of our examples that we're going to finish talking about in this talk, they will be commutative rings. When rings are not commutative, you can still do stuff, but all kinds of stuff starts getting weird very quickly when it's a non-commutative ring.
Would a vector space be a ring?
A vector
Or a
space?
vector field?
Not in general, because you don't have a multiplication operation.
Right.
You have a dot product or whatever, but the dot product of 2 vectors is a scalar and not another vector, right? Even in the case of, again, like specifically R3 equipped with a cross product, so you could call that a multiplication. It would be non-commutative. I'd have to think for a second, but I think it fails.
No, it's got no identity.
Well, it has an additive identity. It doesn't have multiplicative, but you don't need that for a ring.
Okay.
You call those a rung
Distance.
with no I.
Yeah, I actually, when I was looking this up, I actually saw that term. I feel like I probably saw it like 10 years ago, but I saw it again and I thought it amused me for a moment. I would have to think about it a little bit more. So like vectors with like the cross product, that's an addition, that is a multiplication. I would have to think about it more. I think, doesn't the cross product fail associativity or something like that? Or I would have to look it up. I think there's some sort of property of the cross product that doesn't quite work out like you would want a regular multiplication to work out. I would have to think about it a little bit more.
Could you use like a tensor product or a wedge product in place of the cross product?
I mean, if you want to start talking about stuff like that, you can define all kinds of ridiculous abstract algebraic structures, some of which, yes, would very well be rings of various types.
The groups and whatnot, but I don't know if you get a full-fledged ring.
Yeah. I studiously avoided the word group in the entirety of this book. You should have started with fields and working down instead of the other way around.
Right.
I'm so sorry. I'm trying to keep up.
Yeah.
It is zeros. So for complex numbers, you're able to get back to -1 at some point, right? So wouldn't that technically be open because you're able to get back to a real number?
Well, so all it means to say that C is algebraically closed is that if I write for you a polynomial whose coefficients come from the complex numbers or somewhere below, and I ask you what are the zeros of that polynomial, you can always find them here or maybe earlier. Okay? So that is, if I give you if I give you a polynomial in the complex numbers and I ask you to find all the zeros, the answer cannot possibly be, well, there's a zero that doesn't exist here, you have to invent an even bigger set to find the zeros. That can't happen, right? So for the real numbers, sometimes you need to go to a bigger set to find the zeros, right? For the complex numbers, you never need to go to a bigger set to find all of the zeros.
Okay.
Would you ever have to go into the quaternion?
The what?
The quaternion.
Say it again?
Are they pronounced quaternion?
Oh, the quaternion. Okay, that's all right.
J squared plus 1 is equal to
Not for, if you're talking about like as far as finding zeros of complex numbers, no. The quaternions are their own structure and stuff, but if we're specifically talking about zeros of polynomials with complex coefficients, they're all in the set of complex numbers. You never need the J and the K and stuff that would come up in the quaternions.
They also fail commutativity and a few other things. So even if you did have something like, J squared, K squared is -1.
Yeah,
that
yeah.
satisfies the polynomial, but.
Yeah, the quaternions aren't a field anyway,
Yeah.
so, yeah. So, okay, so ring, right, so multiplication doesn't need to be commutative, but in the examples, like, we're gonna use the complex numbers, except mostly it will be commutative. In a ring, you don't necessarily, you still have additive inverses, so every number has some other number that adds up to give you 0. You don't necessarily need to have multiplicative inverses in a ring. Another way to say that is, in a field, you have to be able to divide. In a ring, you don't necessarily have to be able to do division. So for example, probably the most familiar example of a ring which is not a field, the integers. So the set of integers, right? 0, plus or minus 1, plus or minus 2, so on, right? That is a ring. It's a commutative ring under the regular operations of addition and multiplication, right? Addition of integers is commutative, multiplication of integers is commutative. If you add or multiply any two integers, you get another integer, right? There is a 0, right? There is an additive identity, 0 plus anything gives you that thing back. But you don't necessarily have, you can't necessarily divide in the integers while remaining within the set of integers, right? For example, the number 2 is an integer, right? Just knowing what we know about numbers, the multiplicative inverse of 2 is 1/2. That is not an integer, right? So within the set of integers, the number 2, and in fact, there's not really anything special about 2. Only 1 and -1 have inverses in the integers, right? Every other integer, right, its reciprocal, its multiplicative inverse, is no longer an integer, right? So the integers are not a field because the multiplicative inverse of an integer does not need to still be an integer.
So they're a ring, not a field.
It is a ring, and it's a commutative ring because the multiplication is commutative, but it is not a field.
So your definition there, a ring doesn't have to be a field?
Every field is a ring, but not every ring is a field.
Okay.
Because essentially, like, a ring is a field where you've gotten rid of some of the requirements, so if you're no longer meeting those requirements, it's not a field anymore, but it is a ring. So familiar, so basically what I just said on the board there, right? Another example of a ring, which is important for what we're discussing here. So suppose I start with any, so I say R here is any commutative ring. Right, so maybe it's the integers, or maybe it's, again, fields count as rings, so maybe it's the real numbers, the complex numbers, the rational numbers, whatever, right? So some commutative ring, right? So we used this notation a little bit ago, right? Right here, Rx, so that's the set of polynomials with coefficients that come out of that ring R. that is also a commutative ring. So if R is a commutative ring, the polynomials with coefficients in R, with the regular operations of polynomial addition and multiplication, form a ring, a commutative ring. Right, you can multiply polynomials in either order, you still get a polynomial when you add them, right? You have negatives of polynomials. Again, not generally a field, right? Even if R itself was a field to start with, right? This polynomial ring cannot be a field because the variable x, 1 over x is never, right? 1 over x is not a polynomial, right? So the variable x does not have a, you can't divide by x in the polynomial ring, right? So it's not a field. So you have a ring, you have the polynomials in one variable, that's also a commutative ring. If you iterate that idea, that immediately means that you could actually attach any finite number of variables and it's still a commutative ring because, right, so that's a ring, so that's a commutative ring. Okay, take that one and attach a second variable, right? Should still be a ring by the same argument, right? Attach another variable, still a commutative ring by the same argument, and so on and so on and so on, right? So the set of polynomials with coefficients in a commutative ring with any finite number of variables is still going to be a commutative ring. And that's a fact that we need, right? Because if you remember, what we would like to talk about is polynomials with multiple variables like that. So we need the fact that that's a ring. Rings.
I don't know if I'm saying this correctly, but every field is a ring, but not every ring are fields.
Right, right. It's like the same idea, right? Like if you think about it, like every integer is a rational number, but not every rational number is an integer, right? It's a kind of like that same sort of idea.
There's like the little Russian dolls, yeah, like the nesting doll.
Kind of, yeah. Okay. So to really discuss, is this screen crooked? Yeah, I was thinking that. Crooked. I think I remember teaching this room, but yeah, that screen is kind of crooked. Anyway,
Did you fix it by touching it?
it's
Just feel like Mario.
Andrew, you're tall.
It's good enough. As though someone touches it, it'll probably flip upside down or something like that. Okay, so abstract algebra, the study of like these field and ring structures and stuff, there's tons that can be said about it. For algebraic geometry, we need a notion of, it's not coming up here, a notion of something referred to as an ideal in a ring. So, let's see, a subset of a commutative ring. So you have, say, right, so I call it J here, right? So say J is a subset. J is inside of your ring, right? It's called a subring if it itself acts as a ring under the same operations, right? So you take the same addition and multiplication from R, apply them to that subset. If it still works as a ring, you call it a subring of the main ring. Specifically what that means is that if you add two elements, so if you have two elements in that subset, if you add or subtract them, they still have to be in that subset. And specifically, a ring has to have 0. So 0 is in the set. So, and I guess multiplication as well, right? You multiply two elements, that it still has to be there as well, right? So addition, subtraction, multiplication, 0 exists in the set. That's referred to as a subring. I don't think I specified this that much on the previous slide. 1 does not have to be in a sub. Technically, the number 1 does not have to be in a ring, which again can do weird stuff when that happens. But I'm not specifying that 1 has to be in the subring here, and I'm doing that for a very specific reason. So what I want a subring with a specific extra property. So J is inside of R, it's a ring in its own right. I want to have an extra stronger property, right? So since J is a ring, if you multiply two elements in J, it still has to be in J. To be an ideal, so kind of intuitively what you can say is that to be an ideal, this subring has to absorb multiplication by any element of the ring. So not only is it true that two products of J have to be in J, if you want this to also be an ideal, what you have to have is that if you take any element from the ring and any element from your subset and you multiply them together, the result lands in your subset still. An example of that's probably not too hard to understand, if you have like the set of integers, then something like the set of all numbers that are divisible by some particular integer, that's going to be an ideal. So like say, the way something like that might often be written is like this: the ideal generated by 4, that would stand for the set of all numbers in the integers that are divisible by 4. So everything that looks like 4 times k for some integer k, right? So, right, why is that an ideal? Because if I take any number that looks like 4 times k, and I multiply it by any integer whatsoever, it doesn't matter, just pick any random integer, right? Well, whatever that works out to, I think that's right? Right, that's still going to be divisible by 4, right? Because the 4 is still there, that's still divisible by 4, right? So you take any number divisible by 4, multiply by anything whatsoever, any integer whatsoever, it's still divisible by 4, right? So that's an example of an ideal, right? I could take anything in this set, multiply by any integer, the result is still going to be in that set, okay? Ideals are really important to the study of abstract algebra in general. What I need for the correspondence we're going for here is this definition here. The radical of an ideal is defined, so they use kind of the radical, the square root symbol, right? The radical of an ideal is defined, so here, let me write this down. Right, so you have subideal J, radical J is the set of all elements in your ring such that some power of that element ends up being in your ideal J, right? So it is very much like the idea of extracting radicals in just like algebra and stuff, right? It's like you're taking the set of all possible square roots and third roots and fourth roots and stuff of elements that are in your ideal, okay? That's referred to as the radical of an ideal. And I point out here, if you start with an ideal, the radical of that ideal is itself still going to be an ideal as well. And I think I have one more definition right there. If an ideal is equal to its own radical, so like you start with an ideal, you try to calculate the radical, and it ends up being itself. Right, because what's always true, right, if you have any element in your ideal, its first power is in the ideal, right? So any ideal is always inside of its own radical. It's possible that the radical is not actually bigger than the original ideal. It's possible that they're actually the same. That you start with an ideal, you calculate the radical, and oh, it's the same one you started with. In that case, you call the ideal a radical ideal. Okay, so with a million years of terminology, we essentially have enough at this point to say what is kind of the very interesting connection between these algebraic sets, these geometric zero sets, and the structures, these structures specifically of ideals inside these polynomial rings. Let's give one more definition that it's sort of like a geometric definition, but we couldn't really have given it yet without talking about the word ideal. So if we have, we have our affine space again, right? And we have some subset of that affine space. We define the ideal of this set to be, so we write it like this, the ideal of y. That is the set of all polynomials in the polynomial ring such that, so y is a set of points, right? If you have any polynomial that becomes 0 when you plug all of those points in, you say it's in the ideal of that set. So if you have a polynomial that you get 0 if you plug in any element of this set y, that you say that that polynomial is in the ideal of the set y. So the ideal of y, right? The ideal of y is a collection of polynomials. It's a subset of the polynomial ring, and maybe not too surprising based on the terminology, the ideal of a set is an ideal of the ring as we just defined. Note that this is in fact an ideal of the ring. Okay, and a little explanation of why, but okay. So what we have at this point, sort of putting together everything we've talked about, right? We have the polynomial ring in n variables, and we have affine n space over that same field, right? In the same right, the same n, right? Same number of variables as the dimension of the affine space. We have these two functions that we called z and I over the last number of slides, right? So we have this function z that takes, if you have a subset of the polynomial ring, it gives you the 0 set of those polynomials, right? It gives you the set of all points over here. That is the common zeros of those. And we have this other function, this ideal function that we just defined on the last slide, I, which is a function going this way, right? That takes any subset of an, right? I take a subset of an, and it maps it over here to what we just called the ideal of that set, right? So we have a subset of polynomials. We can correspond it over to a set of points in affine space. We have a set of points in affine space. We can define an ideal in the ring that it is associated to, right? So this theorem says, this theorem is pretty straightforward. What this theorem says, so there's 2 bullet points there. So this one says, so suppose you have 2 subsets in the polynomial ring, right? So T1 is a set of polynomials, T2 is a set of polynomials, and T1 is inside of T2, right? What this claims here is that if I ask, what is the 0 set of this one? What is the 0 set of this one? It reverses which one is included. So if T1 is inside of T2, the 0 set of T2 is inside the 0 set of T1. And I think that's not too hard to explain because, again, the 0 set of T1 is the set of all points the set of all points that when you plug them into the polynomials in T1, you get 0, right? Same thing for T2. So if you have if you have an element in here, z of t2, right? So you have a polynomial that becomes 0 if you plug in any point of t2. Well, t1 is inside of t2, right? So if your polynomial is 0 when you plug in everything here, it certainly has to be 0 when you plug in everything in the smaller set, right? So if a polynomial is in the 0 set of t2, it ends up having to be in the 0 set of t1. So reverses which way the inclusion goes. The ideal operation, this I1, works the same as well. If I have two subsets of the affine space here, say, y1 and y2 there, then if I say the ideal of y1, the ideal of y2, those sets inside the polynomial ring, that reverses the inclusion as well. Again, it's a similar idea, right? Suppose you have something in the ideal of y2. If you have something in the ideal of y2, that means that you are looking at a polynomial that becomes 0 if you plug in any point of y2. But then that means it also becomes 0 if you plug in any point of y1, and so it must be in the ideal of y1 as well. So the fact that those reverse is, I mean, it takes a little bit of saying why it is, but that's not really the super exciting part. I forgot I actually typed the reasoning in here as well. So what I just said out loud is basically right there as well. Okay. So this theorem right here, and we'll write on the next slide here kind of a different way of saying it and another consequence of it. This is the theorem that sort of makes algebraic geometry work. So okay, we have these relationships, 0 sets and ideals and stuff, but okay, what do they do? Who cares? What do they tell you, right? So we need this theorem here, which I will not try to explain and prove because it's much more involved. Hilbert's Nullstellensatz? Very German, right? It looks like one of those words that you're supposed to scream in a very angry German. Nullstellensatz, right? The translation, Nullstellensatz essentially stands for theorem of zeros, or I think a little bit more literally zero locus theorem or something like that is what that word translates to. So what this says is that, K be an algebraically closed field like the complex numbers. Suppose you have an ideal inside the polynomial ring. And suppose you have a polynomial that is in this ring. You have a polynomial that's in this ring that vanishes at all points of z of j. So for any point in the 0 set of this ideal that we mentioned, plug it into this polynomial, you get 0. Okay? Hilbert's Nullstellensatz states that if that's true, then there must be some positive integer, or well, non-negative, I guess, 0, 1, 2, 3, 4, 5, such that, so if this is true, then what the Nullstellensatz says is that some power of this polynomial is actually in the ideal j itself for some particular power. It doesn't tell you what the power is, but it tells you at some point that at some point some power of that polynomial has to land back inside of that ideal. Another way of saying this, I think I say this on the next slide, restating this with the terminology of the radical of an ideal that we talked about just a minute ago. So if I'm saying that, okay, it must be the case that some power of f is in the ideal j, that's the same thing as saying that f is in the radical of j, right? Some power is in J, F is a root of something in J, right? Okay, so that theorem is, at first doesn't really sound necessarily all that exciting, but if we sort of try to unpack what it's saying, with some of the, unpack what it's saying with some of the terminology that we've seen so far, we get some very interesting conclusions. So this is what I just wrote on the board, right? The claim from the previous theorem is equivalent to saying that F would be in the radical of J. Using all of our vocabulary so far, we can restate this theorem as saying that the we can restate the N.E.R.D.S as saying that the ideal of the zero set of J is the radical of J. Right, so, right, back up here, right, we declared that F was a polynomial such that if I plugged in any point from this set, you got 0, right? That's what we defined as the ideal of a set a little while ago, right? So this here, right, for any point in the 0 set of J, F of P is 0. I could rephrase that as saying that the polynomial F is in the ideal of this set. And according to what we just said about the radical, that is the radical. So the N.E.R.D. says, saying it this way, the ideal of a zero set of J is the radical of that ideal. So what that means we have. So in particular, right? So in particular, if you have a radical ideal, an ideal which is its own radical, then the fact that this comes out to radical J, if J is its own radical, then it's almost like the ideal operation and the zero set operation are like inverses or something, undoing each other, as long as J is a radical ideal, right? So what we have is this, that these functions z and I, the zero set operation, the ideal operation, give us between the affine space, which I don't right the adding right, affine space, polynomial ring, same number of variables. Right, we have the zero set operation that goes this way, right? You have a collection of polynomials. You can talk about the common zeros in affine space. You have the ideal operation that goes this way. You have a set of points in affine space. You can talk about the ideal, the collection of polynomials that that all those points satisfy. And what we are seeing here, right, based on here, let me rewrite this right here from the previous slide. So again, right, using this fact that we had on the last slide, right? I of z of j equals radical j. Right, so using that fact, right, so here, let me actually write this way. Let me write in words. So if j is a radical ideal, then, right, so that comes out to the radical of j, but if j is its own radical, that just gives you the same ideal back, right? So there is a one-to-one inclusion reversing correspondence between algebraic sets in the affine space and radical ideals in this space here. So whenever you have an algebraic set, you can apply the ideal operation and discuss the radical ideal that is related to it. If you have a radical ideal, you can apply the zero set operator and discuss the zero set of polynomials. And the reason that that's interesting is, and this isn't the only area of math where this happens, whenever you have something in math, a correspondence like this, it often opens the door to allowing you to do things like, if I want to figure out something about the geometry of what's going on in this space, using this correspondence, maybe I can do it by figuring out something that's happening with the algebra over here, and then therefore whatever happens on this side, right? Or vice versa. If I would like to figure out something with the algebra, maybe it's easier to work with the geometry, and then by the correspondence say, oh, well then the thing I want to show must be true, because it's true on the geometric side, right? So this fundamental relationship is the basis of the study of algebraic geometry. And I finish up here with just like a few examples of like, just with this basic relationship and without saying a ton more, some examples of some things that we could say using this idea. So this fact here isn't really all that exciting, but I need to say this for a different fact later. So in the polynomial ring, I say here the biggest ideal in the ring is, it's always true that if you have a ring, the entire ring is an ideal of the ring. So the biggest ideal in the ring is the ring itself, right? This relationship reverses the inclusion, right? So the biggest possible radical ideal here must correspond to the smallest possible, right? So the biggest possible radical ideal, since you're reversing the order, corresponds to the smallest possible algebraic set. So that means that the zero set of the entire ring is the empty set, because as we mentioned earlier, the empty set is an algebraic set. And vice versa, the ideal of the empty set gives you the entire ring back. Okay, there's a lot of text on this slide. There's a definition at the top of a particular, there's lots of different types of ideals in rings. One definition is a maximal ideal. So an ideal in a ring is called a maximal ideal if there is no other ideal bigger than it other than the entire ring itself, okay? So it's the biggest possible ideal you could get other than the entire ring. So, right, you have your polynomial ring, right? You have, did I call it M? Yeah. You have your maximal ideal inside of that, right? Which is the biggest ideal, there's no other ideals in between, right? So according to our correspondence, right, the zero set, the ideal correspondence, so as I said on the last slide, so inside the polynomial ring, and inside affine space, the entire ring corresponds to the empty algebraic set. And again, by the way the order is being reversed, a maximal ideal would have to correspond to the smallest possible non-empty algebraic set. Right, so it can't be empty because that's that one, but it has to be the next smallest possibility, right? What would be the next smallest possibility for an algebraic set? A single point, right? So the smallest possible non-empty algebraic set is always going to be a set that consists of like one specific point like this, say like A1, A2 up to AN or something. Why is that? Because that would be the zero set if I took this collection of polynomials, x1 minus a1, x2 minus a2, all the way to xn minus an, right? Plug in a1 for x1, that gives you 0. Plug in a2 for x2, that gives you 0, and so on and so on. And that's the only point that could possibly give you 0 in all of those polynomials, because each of those numbers is the only 0 of each individual polynomial. So the smallest possible non-empty algebraic set is a point. So a maximal ideal corresponds to the smallest possible non-empty algebraic set. So, right, so I guess write it that way, right? So the 0 set of M is this single point. So the 0 set of M is that single point. So then that means that all of these polynomials then, if I take the ideal of the 0 set of M, here, let me write it this way. Right, again, the ideal of a set is the collection of polynomials that become 0 on that set. All of these polynomials become 0 on that set, right? Because they satisfy that, that's the set. So all of these polynomials are in that ideal. As we said with our relationship, right, the ideal of the 0 set of an ideal is the radical of that ideal. Let me not try to belabor the point a little bit. The radical of a maximal ideal is always itself. The radical of an ideal is always, I think I said this before, it has to be bigger than the original ideal, but if it's already a maximal ideal, you can't really get bigger, right? So all of these polynomials happen to be in M, but it can be shown that these polynomials themselves, they actually do have to make a maximal ideal by themselves. You use the word generate. Generate a maximal ideal. So not only are those polynomials in the ideal M, the ideal M must actually just be the ideal that you get by the ideal generated, that is all possible combinations of those polynomials. So that is, what we've shown is that in your polynomial ring, any maximal ideal always can be formed like this. So take your first variable minus some particular constant, your second variable minus some particular constant, your last variable minus some particular constant. That proves that every maximal ideal in that polynomial ring has to look like that, right? So you're using this notion of a point in geometry being the smallest possible algebraic set to turn around and prove an algebra fact about what a maximal ideal has to look like, right? I think I have like 1 or 2 more examples here. Yeah. I put it there, I told you. Let's see. Suppose J is a radical ideal in your polynomial ring, and it's not the entire ring, okay? There's a terminology here. If you have an ideal that's not equal to the entire ring, you call it a proper ideal. Similar to like with subsets, right? A subset that's not the entire set, you call it a proper subset, right? So suppose you have a proper ideal, a proper radical ideal. Then,
Quick question. Does that say 20 out of 44
where?
on the side?
Yeah.
Oh, okay. Just checking on that. Just seeing about that.
I don't know what the out of 44 means. Because this
Slides?
well, this is the end right here. And
Oh, is it?
and it says 21 out of 44, so I'm not really
Right.
sure.
Okay. All
I
right.
think
Just wondering about what that 44 meant.
I think what it might be doing is like, so on some of the slides I had a pause, right? And then yeah. Notice how it's not, it says 18, it still says
Right.
18, still says 18.
Right. So there's 44 including pauses.
Yeah, I assume that's probably what it means, yeah. So last couple of examples here. So, okay, so let me,
Seeing how the data should be.
Too much information.
okay, so again, right, our entire polynomial ring corresponds to the empty algebraic set. So now I'm saying up here, suppose we have a radical ideal, and it's not equal to the entire ring, right? So it's definitely a subring, subideal. So, as we've said a few times, right, the entire polynomial ring corresponds to the empty set. So then this radical ideal under the same relationship, well, what does it correspond to? Well, I don't know what that ideal is, right? So I can't say exactly, but I can tell you what it can't correspond to, the empty set, right? Because it's a one-to-one correspondence, right? So I don't know what exactly this is, but it's not the empty set, right? So that is, right, so the function that goes this way, that's the zero set function, right? So I'm saying that the zero set of this ideal can't not be empty, right? So what that means is if you have any collection of polynomials, so for any proper ideal J, the set of common zeros of those polynomials cannot be empty, or to rephrase that, there must be at least one common zero for any subproper radical ideal of polynomials. So it is not possible to take a proper subset there and then say, oh, there are no common zeros whatsoever. That can't happen. For any proper ideal J, there must exist at least one common zero for all the polynomials in it. Which again is a fact I would say just from the geometry. Okay, you have a collection of 20 polynomials here. Is it obvious that they must have a common zero? I would argue no. But with this framework and this relationship, it becomes immediately obvious that that has to be the case. One more final example I have here that's omitted. So, kind of continuing on, so maybe let me erase, but it is still right there. Continuing on from this up here, right? So, any proper ideal, the zero set cannot be empty, right? So what if we specialize this? So instead of looking at some arbitrary algebraically closed field K and some arbitrary number of polynomials, suppose we took the complex numbers to be our algebraically closed field, and suppose we wanted to discuss polynomials in just one variable over the set of complex numbers, right? Suppose that, so I say here, suppose f is a polynomial in that set, and suppose that the degree of f is 1 or bigger. So f is not a constant polynomial, right? So degree 1, degree 2, degree 3, just it's not constant. So let me go right there. F is not constant. Okay. I sort of used this term a little bit ago, the ideal generated by something, but let's say it again. The ideal generated by f, this is a pretty common notation. That means the set of all possible multiples of f. So the set of all polynomials you can get by multiplying f by any polynomial from your ring up here. So, right, essentially the set of all polynomials that are divisible by f, if you wanted to say it that way, right? So that's what that set would look like. I know that this set cannot be the entirety of the polynomial ring. For example, I know that 1 cannot be in this set. How do I know that? Because the degree of f is 1 or bigger, and when you multiply polynomials, their degrees add, right? So G times F, what would be the degree of that? It would be the degree of F, which is 1, plus whatever the degree of G is. So that result is still going to have degree 1 or bigger. So you can't get 1 or any constant polynomial for that matter in this ideal, right? So 1 is not in this set, but 1 is in this set. So that means that this ideal is not actually, it can't be the entire set, right? So you have your entire set of polynomials. You have this ideal, which it must be strictly smaller. They cannot be the same thing, right? Under our correspondence, again, for like a bit of time at this point, but under our correspondence, the entire polynomial ring, the algebraic set it corresponds to is the empty set. So this ideal is going to have to correspond to a non-empty set, right? So that is the zero set operation. The zero set of that polynomial cannot be empty. Or to say that in words, this polynomial has to have at least 1 0 in the complex numbers. Right, because it's zero set's not empty, so there has to be at least one thing in it. And this statement that if you have a polynomial in the complex numbers with degree at least 1, and it must always have at least 1 0, that is the statement of the fundamental theorem of algebra. So another use for this, you can prove the fundamental theorem of algebra via this relationship as well, which is very interesting. The fundamental theorem of algebra has many different proofs, but this is a very interesting one making use of this, this correspondence. So, thank you for coming. I hope taking it at a level where, like, I know there's a lot of terminology and definitions. Try to say things in a way that, like, was followable.
That was so good.
Does anybody have any questions at all?
Is there a way that you can, or no, how does topology connect to this, if at all?
You know,
'Cause
I started, like, if you look at the LaTeX file, there's about 3 slides commented out where I started talking about the Zariski topology. So I left that out on purpose to not, it's already obtuse enough, right? So topology is, in case anybody doesn't know, topology is another area of math that is, how would you define topology? It's the area of math that is concerned with properties of figures that remain constant under continuous deformations of the shape. So where topology comes in is, so we have these, so if you have a set, right, you can define a topology on a set by defining what are called open sets, and then their complements are closed sets, or vice versa. And they have to satisfy a couple of properties. So the closed sets have to satisfy the property that the union of 2 closed sets is still closed. If you're defining a topology, the intersection of any number of closed sets still has to be closed. And the entire set and the empty set have to be closed. So if you can define a collection of subsets on a set that have those properties, those would define what you would call the collection of closed sets of a topology on that set. As it turns out, if you have, so the algebraic sets that we were talking about, right, the 0 sets of some collection of polynomials, the union of 2 algebraic sets is still an algebraic set. The intersection of any family of algebraic sets is still an algebraic set. And as we mentioned, both the empty set and the entire affine space are also algebraic sets. So the algebraic sets satisfy all the criteria you need to say that they form a topology on the affine space. So the algebraic sets are the closed sets of a topology on your affine space, and that topology is referred to as the Zariski topology. And that is very heavily examined and looked at in algebra. If you're doing algebraic geometry, you're often going back to that topology and trying to look at properties of it. For this talk, I tried to, because it's just another layer of nonsense that probably didn't need to be included. Again, like I just said, I started typing a few slides of it, and then I was like, Jesus Christ, this is getting ridiculous.
And also your algebraic zero sets, right, have Betty numbers that you could attach to them. You could say like, oh, there are this many components, there are this many holes in my set.
Right. So that's I showed like a few basic, or if you want to call them basic or not, I don't know, results at the end of this presentation from the connection, right? But once you bring the topology in, this study of like things that were made invariant under transformations and stuff, that's where you really get to start talking about the specifics of the geometric structures of these zero sets and stuff like that. So you have this link between algebra and geometry. To make full use of it, you need to bring in that topology aspect as well.
So could you go from this to like a Klein bubble or like a Mobius strip?
I'm sure
And
you
then
could, right?
They're shapes and they have surfaces.
I mean, because the Klein ball is defined by a polynomial equation, or
I think you probably most easily get there by sliding through projective space, because that's where the Klein bottle naturally lives. But if you want like a zero set that gives you a Mobius strip, you can check, what's his name? Differential Geometry, Volume 1 by Spivak has a system of equations that produces a Mobius strip in like as a zero set of polynomials. So you can get there. It's running interference for you.
that's why I don't know off the top of my head, like if the Mobius strip could be developed with a polynomial system.
Yeah. I've seen it in Spivak. It's really, it's it.
Okay.
It's nice if you want like something you can do calculus on that's also a Mobius strip.
You're the president of the
Yes.
N.E.R.D.S.
Any other questions? Random wonderings?
Let's thank the speaker one more time.
And again, thank you all for coming.
It was really good.
Can I ask you some the proof slide of the Yeah.
You would take a t-shirt, you keep folding it, boom, the geometry changes. I don't know. Why is it called differential equation?
It's like basic stuff and no. I was thinking with respect to what it gets.
You're a big bad.